Hello, this is Jonathan Templin from Clemson, and this is a lecture on principal components analysis, exploratory factor analysis, and conducting exploratory factor analysis with CFA. So let's get started. In today's class, or this lecture, we'll talk about methods for exploratory factor analysis that are principal components based, maximum likelihood based, and how things fit in together. Then we'll do some comparisons of confirmatory and exploratory factor analyses, and how to conduct exploratory analyses with confirmatory factor analysis itself. The logic of exploratory analyses is somewhat interesting. They attempt to discover hidden structure in data with very little user input. What could go wrong? Basically, the idea being your input will be your data. You had to decide how to collect that, but then as you use some type of software, you'd have to pick the type of analysis and the estimation method to do so, get results with. The results, though, from exploratory analyses can be misleading. It sounds pretty nice. Hey, let's let the machine or let this algorithm determine exactly how, let's say, questionnaire data tend to have items be correlated. That's one way of putting it. Doesn't always work as well as expected. It's not quite as clean, and that's where things become a little problematic. If your data don't meet the assumptions of the model or the method you select, you can get wrong answers. I've heard that one before. If your data have quirks that are idiosyncratic to the sample selected, maybe you have some outlying cases or you have some groups of people that respond in certain ways. Again, if you have cases that are extreme relative to others, outliers in a multivariate sense, or if you make some constraints on the analysis that are implausible. And more about that as we go into this class about what we're actually constraining there. But sometimes exploratory analyses are needed, right? Sometimes you need to construct an analysis that capitalizes on the known features of the data, and there are better ways for doing that, and that's what I hope to end this lecture with. But oftentimes, exploratory analyses are not needed, right? But are conducted anyway. So think of it this way. Let's imagine you have a concept you really would understand and like to measure. Let's take a personality trait like, happiness or something like that. You have studied the field of what happiness is. You've created a bunch of items that seem consistent with that identification. You believe that there's one dimension, and you go and estimate your model as such. The methods that you would use in confirmatory factor analysis basically seek to falsify that model that you put into place, to basically disconfirm whether you have a one-factor model. That is a much more powerful way of doing analyses, as opposed to using a method like you see here, which is, I don't know how many things I'm measuring, despite the fact you put into time and effort into actually building an instrument to measure those. And you may end up having results that just don't make sense. So that's sort of the downside of exploratory analyses. It's difficult to expect your data to tell you exactly how they should behave. You are the one who are creating things that to use these analyses for. But we'll start, though, with principal components. And to do that, we'll have to talk a little bit about more advanced matrix algebra. So to begin this section, it's because matrices are not exactly obvious or intuitive to most people. Let's start a little guiding example. I generated some simulated data to pretend we had SAT scores for math and verbal for 1,000 students. And you can see descriptive statistics of this. Basically, the mean for each is right about 500. The standard deviation varies from each. And you'll see a high correlation of 0.78. One thing we need to define is the trace of a matrix. So if you have a square matrix with the total number of, I'll use the little letter P to denote the number of columns and rows. Remember, a square matrix is one where the number of rows is equal to the number of columns. We define the matrix trace as the sum of the diagonal elements. You go down the diagonal and you add up all those values right there. So that matrix here. For our data, the trace of the correlation matrix is 2. So this is a square symmetric matrix. We just add the diagonal right there. 1 plus 1 is 2. In fact, for all correlation matrices, the trace is equal to the number of variables, as all diagonal elements have to be 1 in a correlation matrix. We use the trace, though, as we define this as the total variance. in a principal components analysis. Basically, what we want to show is that how we reconfigure our data leads to these new components. These are sums of weighted variables. And we want to show that basically we account for a large percentage of the total variance. It's a target we're trying to recover when we apply these models. Next, we want to talk about a matrix determinant. A square matrix can be characterized by a scalar. It's called a determinant, or for a scalar, it's just a single number. We denote determinant using the words det sometimes, or putting a matrix within 2 bars. Turns out the calculation of the determinant by hand is quite tedious. The determinant of our correlation matrix, for instance, was 0.3916, and actually in a 2 by 2 square matrix, it's not that tedious. It gets much more tedious as you increase the number of rows or columns. Now, the determinant itself, computers actually have struggles. I wouldn't say difficulties, but they can compute it just fine. And there's a bunch of rounding error. It has a lot of operations to go and get a determinant usually. But we use the determinant in quite a few places in statistics. It shows up in multivariate statistical distributions. We've talked about it in the context of the multivariate normal, for instance. It is a measure of what we call generalized variance. But for us, in our purposes, the main thing is if the determinant is positive, then the matrix is called positive definite and can be inverted. That's important, as you know, because the inverse of the matrix shows up in many places, including the multivariate normal distribution. And if the determinant is not positive, the matrix is called non-positive definite, which means a matrix cannot be inverted using the standard matrix inverse. Now, if the determinant is exactly 0, we call that semi-positive definite. And to me, that is an interesting way of framing things. A semi-positive definite. It's almost like an answer in the affirmative. Hey, how do you feel about having, I don't know, dinner out tonight? I'm semi-positive definite about it. But enough with the poor matrix humor. Another property of the matrices we like to talk about, and this is much more important for principal components, is something that we'd like to define in an orthogonal matrix. All right, a square matrix, let's call a square matrix, this is capital Greek letter lambda, is said to be orthogonal if the following property holds, that the matrix times its transpose is equal to the matrix transpose times it, which is equal to the identity matrix. So orthogonal matrices are characterized by 2 properties. The dot product, or the row of all row vector multiples, is the 0 vector. Remember, to do matrix multiplication, each element of the matrix represents the dot product between the row and column of that respective element from the pre and post multiplying matrices. So what that really means is if you get a 0 there, vectors themselves are orthogonal, which we would say if you look at their angle, vector angle for it, it'd be 90 degrees. Then also, additionally, for each row vector, the sum of all elements is equal to 1. Now, when you do that, when you take a look at all the sum of all elements, what we call that is these vectors are normalized when the sum of all elements equals 1. So the matrix, this is not just orthogonal. Sometimes we call this orthonormal, meaning orthogonal and normalized. Orthogonal having 0 values in the off diagonal, normalized having the diagonal be equal to 1. Now, orthonormal matrices are used in principal components and factor analysis. We will see these very quickly as we get into what we do in principal components. And finally, let's talk about eigenvalues and eigenvectors. This is a really interesting topic. It's very difficult to wrap your head around. In fact, in my own personal history, when I first learned about eigenvalues and eigenvectors, it set me off on this quest to really try to figure out what they were. I went to different classes. I ended up actually in part going to grad school to try to figure this thing out. But that's just me. The eigenvalues and eigenvectors, let's just find this way. A square matrix sigma can be decomposed or re-expressed into a set of eigenvalues lambda. This is a vector of eigenvalues, and a set of eigenvalues e, eigenvectors e, such that the original matrix times that vector eigenvector is equal to an eigenvalue times that eigenvector. Now, each each eigenvalue has a corresponding eigenvector. So these are sort of paired. The number of eigenvalues or eigenvectors is equal to the number of rows or columns. Remember, this is a square matrix sigma. So how many eigenvalues and eigenvectors we get is equal to how many variables are in that matrix, or how many rows or columns. And here's the key, the eigenvectors themselves are all orthogonal, meaning if you take the dot product between any two eigenvectors, the dot product is equal to 0. It means they're uncorrelated. So what that property gives us is the ability to take a lot of data, summarize it with a matrix like a covariance or correlation matrix, and then reduce its dimensionality by taking a smaller set of these eigenvectors. And it turns out that's what we use principal components for. Principal components analysis uses eigenvalues and eigenvectors basically to reconfigure your data. Oftentimes we talk about this as dimensionality reduction. We have 400 variables. It's very difficult to do anything with 400 variables, but if we want to put those, let's say, in a model where we predict some type of outcome, we might first take those 400 variables and boil those down into, let's say, 5 to 10 that explain roughly 90% of the variance, the total variance, the trace of the 400. The added benefit to that is those 5 to 10 that we may get out of this analysis are uncorrelated, meaning as we enter them into a prediction model, they have maximum explanatory power. They don't overlap with each other in the prediction. So principal components analysis is a very useful tool in high dimensional data. And here's an example how it works. So we took our correlation matrix from our our two SAT variables, and we broke that into eigenvalues and eigenvectors. So with two variables in our correlation matrix, we end up getting two eigenvalues and two eigenvectors. The eigenvalues are listed here. The very largest one is 1.78, and the smaller one is 0.22. And two eigenvectors we obtained would be the first one, 0.71 and 0.71, the two elements, and then the second, 0.71, negative 0.71. You can see if we did the dot product, we just multiplied each of these elements and summed them, you'd get 0.71 squared minus 0.71 squared, which sums to 0, showing that. How we did that in R was to first get our correlation matrix and then submit that correlation matrix to the eigenfunction. The symmetric equals true just indicates the correlation matrix is a symmetric matrix. It simplifies the calculations that way. And we got out our eigenvalues and our eigenvectors. Now, oftentimes, this is not the size of data you would like to use principal components on. There's no reason to go and take two variables and reduce them into two uncorrelated components, but this is just to show how the method works. Now, from those eigenvalues and eigenvectors, we can actually reconstruct our correlation matrix with like a smaller bit of information. So basically, that original matrix sigma is equal to the sum of the eigenvalue times the outer product, or the eigenvector times the eigenvector transposed, summed across each of the eigenvectors that you have. So here, what we can do is we can take our very first eigenvalue and our first eigenvector and take the very first, what we call rank 1 approximation to our matrix, and we'd get a matrix of 0.89 that we would get out of it here, just like this. That is, like I said, a rank 1 approximation to our two-dimensional correlation matrix. It is close, but not exact. So this is a way of showing that what we're doing with eigenvalues and eigenvectors is taking a smaller amount of the information, total information available from all the variables. Now, if we take that very first matrix and add to it the second eigenvalue times the second eigenvector times its transpose, what we end up getting back is the full correlation matrix. So what this is called, this sort of decomposition of our matrix into a series of successive sums, it's called the spectral decomposition. And again, it is a way that we can show that our eigenvector eigenvalue process is taking the same amount of information in sigma, right, basically, and reconfiguring it so that as we get closer and closer to the number of total eigenvalues or eigenvectors we have, we better approximate that matrix. And this is the demonstration in R. Now, there are some additional properties of eigenvalues that are useful. So the matrix trace, remember that was the sum of the diagonal elements is the trace. Well, it turns out the sum of the eigenvalues gives us the trace itself. And furthermore, the product of the eigenvalues gives us the determinant of the matrix. Now, the sum of the eigenvalues giving us the trace is what we use to describe how much variance is accounted for, and we'll see that in just a bit as well, too. So that spectral decomposition eigenvalue and eigenvector was an introduction to the introduction to principal components analysis. But now let's put this in the context of PCA, or principal components analysis. Principal components analysis is a method for re-expressing the covariance or often correlation matrix of a set of variables. This re-expression comes from creating a set of new variables, which are linear combinations of the original variables. Remember, linear combinations are weighted sums of variables. So there are two objectives in principal components analysis. The first is data reduction, moving from many original variables down to a few components. Right. So again, that example with 400 variables, if you had 400, you could choose to summarize those 400 with 10 components, 10 linear combinations of the 400. Sometimes also is used for interpretation, right? Determining which original variables contribute most to each component. And the goals of principal components analysis is to find a set of K principal components that are composite variables, right? There are linear combinations that are much smaller in the number of the original V variables you might have, and that account for nearly all the total variance that you end up having in your covariance or correlation matrix. Remember, the total variance is induced by the trace, or the sum of the diagonal. If these two goals can be accomplished, then the set of K principal components contains almost as much information as the original V variables. Think of it as that spectral decomposition that we saw in the previous couple slides. And that means that we can then replace the original variables with these new components in any analysis that we wish to go forward. So principal components analysis is often more a tool that we use to sort of filter data prior to other analyses. And the questions that we ask are typically the following. If we're going to use a principal components analysis, we have to answer these questions really before we really dive into it. The first question is, how many components or new variables are needed to adequately represent the original data? Now, this word adequate is purposefully benign. It is very fuzzy. The term, how many are needed? What is adequate? What does it mean? Does that mean 80% of the variance, total variance, 90%, 40%? Doesn't really well define, but you have to basically use that and describe it as you do an analysis. And then once you finally get this adequate representation, once you decide upon how many variables you need, oftentimes people want to know what each component represents. Now, I wouldn't say oftentimes. If you're using principal components to filter your data to put into a prediction system where you don't really care about why a predicted value is what it is, right? So you just want to make good predictions without explaining, then the second question is not needed. But if you need to explain why it is a prediction does well, that is where you will need to really understand what each component represents. All right, you're creating a weighted sum of variables. What are the weights, basically, and which variables are heavily represented in that sum? So this is also a very subjective or fuzzy concept. So what we end up getting out of principal components is it often reveals relationships between variables that may not have been previously suspected, right? For instance, if you have one component where two weights or weights of two variables are large, but others aren't, you'd say, oh, these two variables somehow play a role in this first dimension. So we get new interpretations of data and variables often coming from this. Right? Again, PCA is a great method for summarizing a lot of multivariate data. But again, principal components analysis often serves more as a means to an end rather than an end itself. We often use this as a filter to reduce the number of variables And then we put those in, multiple regression or ANOVA. We put those new variables in cluster analysis. Now, where it becomes a little bit more difficult is that principal components often get intermixed with exploratory factor analysis. In fact, now exploratory factor analysis sounds, again, very similar in principle, and we'll talk about it as we get later in this lecture. But a lot of times, because we come up with these aggregate sums of variables, people want those to take on factor-like meanings, but it's quite different from a philosophical point of view. Further complicating this is that in the very early days of exploratory factor analysis, back in the 1930s, estimation was done via principal component analysis like matrix decomposition. So basically, we would take a covariance or correlation matrix, and occasionally we would modify the diagonal based on certain things, and then do a principal components analysis on what was remaining. And that would be called, the output would be called an exploratory factor analysis. But as we've learned more about exploratory factor analysis and we've gotten better at model estimation and statistics, that's no longer the case. We no longer need to use principal components like matrix decomposition. In fact, we shouldn't, because the models themselves are very different. The principal components analysis said, let's sum up each of the variables by putting a weight. We call that a summative model, whereas an exploratory factor analysis takes that confirmatory factor analysis idea that the factor causes each of the variables itself. The arrows point the opposite direction, or what we call a reflective model itself. Right? They're not doing the same things. They're not meant to do the same things. So, but they too get intertwined quite a bit. This is me saying, don't use principal components like methods for exploratory factor analysis. They're not likelihood based, which makes them difficult to use when you have missing data. And it just happens all the time, and it's conflated. They are a very technical topic. So this is a very technical thing. Not a lot of people, without studying it, will understand the difference between the two. But it is poor practice right now to really do this, to use principal components in place of exploratory factor analysis. Let's dive back into the details of PCA. Now here, we're going to note that Z, each of these Z variables, are our new components. These are the principal components. And Y would be our original data matrix, right? So our original data matrix would have N observations and V variables. And we'll let the index P be our index for a person, right? So for each person or subject, we have a component score, right? So Z P1 represents the very first component for person 1. How we find that is by taking the first eigenvector transpose times that person's vector of data. And what that ends up giving us is each element, each weight of the eigenvector is our weight for each variable. Each element of the eigenvector is our weight for each variable. So the first element weights the first variable, second element weights the second, and so forth, all the way down to the last weighting the last variable. So you can see, literally, we've just summed our original observations, but put a different weight to each in the sum. Then, again, because we have as many eigenvectors as we have variables in our data set, we can take the second eigenvector and form the second principal component. We can do this all the way down to the last eigenvector, where we make up the last principal component. The weights of the components themselves, these EJK, these little terms right here, come from the eigenvectors of the covariance or correlation matrix. So these things are coming. We basically take our correlation or covariance matrix Y and use that in our analysis to get eigenvectors, and then we get the weights from those eigenvectors. The components are formed, as you just saw, by the weights of the eigenvectors, the covariance or correlation matrix. The variance of a component is actually given by the eigenvalue associated with it, with that eigenvector. So if you go back here, the variance of Z, if we know ZP1, the very first Z, the very first component, the variance of that new component is actually the eigenvalue for it. Right? So it's already built in, tells us how much variance that first component is. And when we couple that with knowing that each successive component has lower variance, it sort of built itself out, then we can actually coupling that with the fact that all components are correlated, we can show that the sum of the variances of the principal components is equal to the total variance, right? The sum of all those variants turns out to be the trace, which is the sum of the eigenvalues. Now, let's take a look at PCA with our correlation matrix. So we take that correlation matrix with the SAT Math, SAT Verbal. And again, this is for demonstration purposes to sort of understand what the process is doing. Here's a scatter plot of the original data that gave rise to that correlation matrix. Again, we use the PRComp function. Actually, we use the PRComp function in R. Remember, in the previous bit of the slides, I used the eigen function. PRComp is a principal components matrix that actually gives us the weighted values themselves. Here, you can see each of the standard deviations for each new component and the rotation itself, or the output, the summary for it. What we end up doing, though, once we go and build our two components, is this. Our original data right here, where SAT Math and SAT Verbal, but once we transform them into principal components, remember the mean of it shifts our data so that we end up centering them right about 0 and reorienting the axes. Right. So now if you look at where the line is between the red line, that is basically a regression slope indicating our correlation, 0.78. Now that line is flat because the two components are uncorrelated. So basically we have rotated our data and centered it about 0. And you'll note the dimension of highest variability is the very first principal component's dimension. The range of values range quite large in that first dimension. And the second dimension happens to be smaller variance. That would be our second component. So now, what does gambling have to do with principal components? Not a whole lot, but we're going to talk about a gambling study that I was part of a long time ago, but it gives us some data to sort of explore how we use principal components with. So as you don't need me to describe this, you probably live in the real world here in the United States. We have had an explosion of gambling in the last 25 years. Now you can gamble on sports on your phone in many states. Heck, you can gamble on political events or world events using sites like Kalshi or Polymarket. Basically, there is no way gambling can infiltrate almost everything in American society, and it's difficult to actually see a way through. Back when the study was done, though, gambling was relatively new. You still had to go to a small set of places to find a casino, and state lotteries were around, but not nearly as pervasive as they are at the moment. Turns out there is a definition. You can have a problem or become a pathological gambler. The Diagnostic and Statistical Manual of Mental Disorders, or the DSM, says to be diagnosed as a pathological gambler, you have to meet 5 of 10 defined criteria, right? So these are the 10 criteria. There are things like very benign, which are you're preoccupied with gambling. And there are things that are quite serious, such as you've committed illegal acts such as forgery, fraud, theft, or embezzlement to finance your gambling. So a lot of different ways of that you could be considered having a problem. So in order to study how pathological gambling sort of grew, it was part of a lab that created a survey called the Gambling Research Instrument. It had 41 Likert type items. There were 6 category items, ranging from strongly disagree to strongly agree. And those items were developed to measure each of these criteria that you see there. Here's some example items. I worry that I'm spending too much time or too much money on gambling. That's criterion 3. Has repeated unsuccessful efforts to cut back, control, or stop gambling. Or there are a few things I'd rather do than gamble, which is criterion 1, being preoccupied with gambling. Now, this instrument was used in a sample of experienced gamblers from a riverboat casino in a flat Midwestern state. It sort of defines a lot of them. Turns out we asked a bunch of casino patrons after they had played roulette to go and answer a survey. But we did pay them so they could have more money to gamble with. There were a 6-point Likert scale. To really meet the assumptions of factor analysis or later on, this would be continuous. We need to treat these continuous. And actually, we had to couple that with 1,192 college students as well. I took 10 items to really show how this works. These are the 10 items that really worked well together on this. And we're going to do a principal components analysis with the 10 items to see if it fits a one factor model itself. Now, to do this, we have to imagine that these were the only 10 items we had and that we wanted to reduce those 10 items into really one or two. But I should note that we should really never use a principal components analysis for this to do factor analysis. Anyway, let's answer number one. How many components do we have? There are two methods that we end up doing this. The first is to look at what we call a scree plot. I'll show that on the next. Basically, we're plotting the eigenvalues in order from largest to smallest. And we're trying to look for a bend or sort of a point of diminishing returns, an elbow to it. Again, I'll show that in the next slide. Second, the other way we could talk about is just coming up with a criterion. Let's say we want to explain 70% of total variance. We can do that by looking at what proportion of variance, the total proportion of variance is sort of taken from it. So here, if we look at the output from our principal components, there are 10 variables, so there'd be 10 components. We have the standard deviation of each component. We have that component's proportion of variance accounted for, and we have our cumulative proportion of variance. So we can see that the first component accounted for 40% of the variance, total variance, the second being 16, and so forth. And cumulatively, we would get about 70% once we get to the fourth principal component. So 75% of total variance was accounted for by the very first four components. If we plotted the eigenvalues themselves, you would see the first four components end up here. This puts a point here, and this bend or this elbow to the scree plot. The word scree is used to describe this plot. It also is a very old word for debris at the end of a cliff. And so that is what this looks at. We're looking at debris at the end of the cliff here. So let's imagine we say, okay, we have four components. What do the components represent? And so here, this is a difficult thing to derive, but this is the value for each weight for each component. And immediately you'd say the very first component has negative values for each of the weights. And that happens. You may see all positive or all negative for that first component a lot of times. Really what we're looking for here, though, is the magnitude. So the variable 14 seems to have the largest negative weight, whereas variable 3 does not. What you're saying there, but each of those is all about the same. So the very first one is almost like an overall average or sum. When we get to the second component, we start to see some really differentiations here. The 14th item, x14, again, is the smallest or the largest in magnitude. It's negative 0.86. It's not related to that component, whereas x18 is. And if we go back to those items, 14 is I'm drawn more by the thrill of gambling than by the money I could win, and 18 is my family, coworkers, or others who are close to me disapprove of my gambling. So it's hard to really understand why this one would be so negative, whereas this would be positive. But that is how you would go about approaching it. Similarly, when you do the same thing for the last components, again, looking at the magnitude, principal component 3 is most unrelated to item 18, and principal component 4 is most unrelated to item 1. Hard to describe what those mean. But those are our final results. And so using the weights of the eigenvectors, we can create these four new variables right here. And this is the values for each one of those individuals in our sample. Now, each of these components are uncorrelated with each other, which is very nice. And we could use this in a different analysis if we wanted to. So in summary, principal components analysis is a data reduction technique that relies upon the mathematical properties of eigenvalues and eigenvectors. We use it to create new variables, a smaller number, out of the old data, where we have lots of variables. And the new variables are called principal components. They are not factor scores themselves. PCA appeared first in the psychometric literature, and many factor analysis methods used variance of PCA before we understood likelihood-based statistics. And you can find principal components analysis as a default option for factor analysis in SPSS and SAS still, if you use those programs. There are a few issues statistically with principal components we can solve. Right? The typical principal components analysis that we're talking about has a few concerns. Some of these can be solved if you know what you're doing, but a lot of times the program defaults don't really resolve these. But what are these issues? First, missing data is omitted using listwise deletion. That is, we're going to have a lecture about missing data, but just know that that's potentially biases are possible. But we could remedy that by using maximum likelihood or missing multiple imputation to go and build our covariance matrix. Second, the distributions of variables can be anything, right? There's no distributional assumptions given, but variables with much larger variances will look like they contribute more to each component. So you could standardize your variables. That might be an easier process to do so. There are many methods where that is sort of required. Finally, the lack of standard errors, right? We get a component weight, but we don't get any uncertainty out of this, but it makes these very difficult to interpret. Now, we can use a different type of approach, like a resampling, a bootstrapping, to get standard errors, but it's not quite easy to do. But there are some other unsolvable issues of principal components analysis. Issues meaning more in its use in interpretation. There are, they really fall under the subjective use of it based on those first two questions of what we'd have to use PCA for. The first is that the number of components needed is not based on a hypothesis test, and it's very subjective, right? Variance accounted for is a descriptive measure, and while you say I might want 70% of the variance accounted for, someone else may want 90, or someone else may be okay with 50, right? So it doesn't necessarily help us. It also doesn't help us test whether an additional component significantly accounts for more variance. And second, the relative meaning of each component is questionable at best and is very subjective. As you notice, as I went through and tried to understand what each component went for, I'd have to go and look at the weights of each variable to it. And so again, if you're trying to really understand what principal components is doing, you roll right into subjectivity, and your choices may not agree with that of others or even reviewers or anywhere else that you're going. So if you're using principal components analysis to really understand your data, it's a difficult proposition. It's very subjective. However, you could also look at the other way, which is I'm just using this to reduce my data, which I have less of an issue with. It's less subjective, and although you still need to understand how many components to use. So next, we will discuss exploratory factor analysis. So similar to some of the ways that we use principal components analysis, you'll see quite a big similarities in exploratory factor analysis. For instance, the primary purpose of EFA is to determine the nature and number of latent variables that account for observed variation and covariance among a set of observed indicators. Remember, indicator is a term that we use for variables that indicate a factor or measure a factor. In other words, what causes these observed responses? We use exploratory factor analysis to summarize patterns of correlation among these observed indicators. And unlike principal components, in exploratory factor analysis, we really want to focus on the solution, the factor loadings, what would look like the eigenvector weights that you would see in principal components. So the solution is an end and is of interest in and of itself. Right? We compare this with principal components, where principal components' purpose is to reduce multiple observed variables into fewer components that summarize their variance, or in PCA, in other words, how can I abbreviate this set of variables, right? Whereas the solution is a means to an end. So in principal components analysis, we want to reduce the number of variables and we want to use those in something else. Whereas in exploratory factor analysis, we really want to understand what those new variables mean. We want to have those take on more meaning itself. Those would be, for instance, latent variables or traits that a person might obtain. So you'll see many different types of methods for quote unquote extraction of factors in EFA. And here's the tip: whenever you're naming a method, let's not name it like we would name dental procedures. It doesn't really go well for marketing. But you'll see many different types of that. We call that extracting factors. It's an interesting way of putting it that way. Many times when you see extraction, we talk about that from a principal components-based analysis. And most of these methods were developed even before computers became relevant. Like, I'm not talking about the widespread adoption of personal computers in the 80s. I'm talking about the development of computers in the first place in the 1940s and 50s, right? So what you end up having are methods that are sort of dinosaurs from a technological perspective. People used to have to compute these as part of their research assistantships in grad school, compute these by hand, right? So I'm going to try to boil that down. Let's just use maximum likelihood for EFA. To me, maximum likelihood is the strongest choice of an estimation method. It has great properties. We can use the same log likelihood as we would in confirmatory factor analysis, and it allows us to estimate our model closest to which the model actually happens to be. There are many who would describe exploratory factor analysis methods using principal components as approximations to what we're doing with maximum likelihood. Approximations is one word. Other pejoratives have been used, or polite pejorative or negative terms. My mentor, Rod McDonald, would call these devices, sort of crude ways to go and estimate variables, estimate models themselves. But maximum likelihood is good for statistical properties. Basically, if you have a large enough sample, you have those great stat properties. If you want a refresher, go find the video on maximum likelihood itself. Second, more importantly, if you have any missing data, it has a much stronger assumption about what the data happen to be. Missing at random, it's a much better assumption for it. It handles data that are missing at random. And it is consistent with modern statistical practices, which largely rely on likelihood functions themselves. So the questions that we ask when using exploratory factor analyses are the same questions posed in PCA, but with different words. So how many latent factors are needed to adequately represent the original data? Right? Adequately means, does a given model fit well? Right? This is in difference in PCA. With how many principal components do we need to adequately summarize our data? And once you answer the question number one, then you then want to determine what each factor ends up representing. And again, this is a very subjective term. I would argue that in factor analysis, particularly when we look at confirmatory factor analysis methods, we have a better sense of how many latent factors are needed to fit data because we have model fit statistics. So number one gets less fuzzy if we use likelihood-based exploratory factor analysis. But even then, number two becomes difficult to really see. So the factor analysis syntax works by hypothesizing that a set of latent factors helps to determine a person's response to a set of variables. Right, this can be explained by a system of simultaneous linear models. Again, the factor analysis point of view, if you recall from the confirmatory factor analysis lecture, we'd say that an observation or a observation y for a person is equal to some intercept plus some factor loading times each factor summed across all the factors there are, plus error. So really what we're saying is if we had observed the latent variables, we could then tell you why a person picked the score response they had done. Here, mu is the item intercept, lambda is the factor loading, and because exploratory factor analysis started with using principal components analysis, you'll see that this is often expressed by a series of factors up to q of these, where q could be the number of one factor per variable. Now, we know in factor analysis that's not identified. But again, this is sort of the historical lineage of principal components bearing itself out. Here, I'll just say there's some q factors themselves. The total number actually will depend on the data that you have. Right? Often we can shorten these simultaneous equations into matrices, as you see down here. So how maximum likelihood exploratory factor analysis works is this. It assumes that your data follow a multivariate normal distribution. That is the basis for the log likelihood function itself. The log likelihood function depends on two sets of parameters. Again, a mean vector and a covariance matrix. We've had this as the CFA lecture. It still follows from it, right? The mean vector is saturated. Basically, this comes from our item means themselves. We're going to assume the mean of each factor is zero. So that means when we do that and we assume zero mean for each error, that means the mean for each item turns out to be the item intercept. Now, the covariance matrix, though, is what gives the factor its structure. And EFA models provide for a structure of a covariance matrix. So the covariance matrix is modeled based on how if the hypothetical latent factors cause the data. For an analysis measuring capital F factors, each item in the exploratory factor analysis has one unique variance and has F factor loading. So all factors load onto all items. The initial estimation of factor loadings is conducted based on the assumption of uncorrelated factors. Now, that is a very big and dubious assumption at best. If you are measuring latent variables that are all from the same person, you would expect those to be somewhat correlated in some sense. And when we do all of that, we can show that the parameters of the factor loadings, unique variances, and factor covariances, again, we don't have any of those, but eventually we will show how to have those, combine to give us the covariance matrix back. So our EFA model implied covariance matrix, assuming that the covariance matrix of the factors, this phi matrix right here is identity, boils down to the matrix of factor loadings times the matrix of factor loadings transpose, plus a diagonal matrix of unique variances. Turns out exploratory factor analysis is identified the same way we use as confirmatory factor analysis and path analysis. First, we have to have the number of parameters, model parameters, not exceed the unique elements in the saturated covariance matrix of the data. So we can't have our factor loadings, total number of factor loadings and unique variances exceed how many covariances we can estimate. Right. So for factor analysis with F factors and I items, there are a total of I EFA measurement model parameters. Right. F factor loadings per item plus I unique variances. So as we will see, though, that's not the only model. You also have to have a set of constraints placed on the model itself. So technically speaking, the model is not identified when we estimate all the factor loadings for all of the items. So what we have to end up doing is set our versions of constraints to show how the model will work. Then further, we need to show that each portion of the model to be locally identified. When we estimate all factor loadings, that local identification fails, so we have to put a couple additional constraints in. Now, this is where things get a little bit weird in exploratory factor analysis land. This is to estimate a maximum likelihood exploratory factor analysis. What's often used is a constraint formed by paper by Lawley and Maxwell in 1962, where we say, oh, the factor loading matrix transpose times our diagonal matrix of unique variances times our factor loading matrix, that resulting matrix from this product, delta, is diagonal, which is an odd way of thinking about it, but basically think of it this way. This matrix here is going to be square and symmetric. So all the terms that would multiply each other would have to give rise to something that had zeros in the off-diagonal elements. By doing that, though, it puts the number of constraints needed to just identify the model itself. And this constraint is not well known, and how it functions is very hard to describe. Well, it turns out in confirmatory factor analysis, we also put constraints on our data. We basically say when we don't estimate a factor loading for an item, what we'd say is that item doesn't measure that specific factor, but that is a constraint that is equivalent, or a model identifying constraint as well. So what I like to think of is when you choose to do the maximum likelihood factor analysis, you have to choose a set of constraints. In exploratory factor analysis, this is what gets used. I'm stumbling over what this means. It's hard to describe. Whereas in confirmatory factor analysis, your constraints come from the structure you're hypothesizing for your data. So I find the confirmatory factor analysis constraints much more believable, much more understandable and interpretable. The other methods, though, of exploratory factor analysis extraction avoid this because they're not statistical models in the first place. We're using matrix properties to resolve this. So here's the thing. Those methods aren't really factor analysis. They are approximations to factor analysis at best. Whereas the methods in maximum likelihood do take a factor analysis model but require constraints. So in my logic, therefore, exploratory factor analysis with this crazy constraint right here, I wouldn't call it crazy, it's well thought out, but it's difficult to describe constraint right here. That thing is much more difficult to understand than a regular confirmatory factor analysis. So I'm building toward exploratory factor analysis, not my favorite method. I don't really advise using it this way. However, I will show you toward the end of this lecture how we can use confirmatory factor analysis to explore our data. Now, this constraint, try to dive into it a little bit deeper. That two-factor, if we had a two-factor, if we tried to estimate a model with two factors, here's what the constraint looks like, right? Here, we're going to sum up for each item the unique variance times the product of loadings has to be equal to 0. That is weird. So some combinations of factor loadings and unique variances themselves can't happen, right? Especially when you think about the unique variances, we take those from the diagonal of our covariance matrix, right? It really constrains what the factor loadings might be. And it's also not a testable hypothesis in CFA. So I really don't like the constraints. That's part of the reason why I don't prefer using exploratory factor analysis, is this is really difficult to describe. Now, our log likelihood function uses our multivariate normal distribution. This is ugly and hard to parse through, but just give me a second to do so. For our data, this is our data log likelihood function. For multivariate normal, here we have our mean vector and our covariance matrix. Under EFA, we replace our mean vector itself with our vector of item intercepts, and we replace the covariance matrix with what the model implied covariance matrix would be here. The matrix of factor loadings times the matrix of factor loadings transpose plus the matrix of unique variances. And again, we need its inverse, so we take the inverse of that. We also need its determinant. So there are a few benefits and consequences of using maximum likelihood EFA. The parameters of the EFA model under maximum likelihood retain the same benefits of any model. So for instance, using maximum likelihood with a large n, asymptotically, they are said to be consistent, asymptotically normal, and efficient, right? So they have small standard errors, they'll follow a normal distribution, and they will converge to their true values as n goes to infinity. Furthermore, if you have an observation or more observation, if you have observations that didn't give you data to some of the questions that you asked, we can still use all the remaining observations in themselves. We can use incomplete observations. We're not using case-wise deletion here. This assumes the data follow a missing at random pattern, which I haven't defined yet, but I will in a few lectures. Furthermore, the same types of model fit indices are available in exploratory factor analysis as are in confirmatory factor analysis. And as with a confirmatory factor analysis, an EFA model must be a close approximation to the saturated model covariance matrix if the parameters are to be believed. So this is a really important part of using maximum likelihood. It falls into the same model fit framework that we saw in confirmatory factor analysis. But this is a very big difference between EFA in maximum likelihood and EFA with principal components-based methods, is this ability to judge model fit. In maximum likelihood, it's much more rigorous. Okay, we're going to start out by looking at maximum likelihood EFA using the base R function factanal. This is not the way I propose. I think you should do this, but I'm going to show you this to you because this does show up frequently, and it's mirrored in other programs like in SPSS or SAS or whatever your favorite is. So the base R program has this function named factanal that conducts maximum likelihood based EFA, but it's very limited. One of its limitations is you can't have missing data. In theory, you can using maximum likelihood, but it was not implemented, so bad R, actually bad function. So we have to remove our cases with missing data. What you're going to see after I do it this way, I'm going to do this again in the way I'm proposing you use, where you don't actually have to remove your data. So this now makes it so that that missing at random assumption, it does not apply, which is not good either. So we're also going to show at first how to use this method without what we call rotation. Rotation is done to try to provide meaning to your estimates. I'm going to show you without rotation to begin with because I want to show that those constraints that we put into EFA are somewhat ridiculous. So this is the code to remove all the missing data you see right here. Number one, we have to first determine how many factors we have. And in the factanal function, you'll see we actually have to do this by increasing factors from 1 and going forward. Now, unlike principal components analysis based methods for EFA, the number of factors is not, the maximum number of factors is not necessarily the maximum number of variables. It's going to be determined by how many parameters are in your model and whether that satisfies the global number of parameters T-rule case, right? So what it will do, though, here is a one-factor solution. It will provide a rudimentary test for model fit. It basically gives you your hypothesis test of your model against the saturated model, like we would see in path analysis or confirmatory factor analysis. However, we know that this test itself is very powerful, and often tends to not fit well. So if this is all you have for model fit, this is all you can use. That's not the case using confirmatory factor analysis, but in Lavon, for instance. So this is going to be sort of an extreme version of pulling out factors from the model. But here's the fit for one factor. You can see the loadings for each factor. This assumes a standardized loading. Uniquenesses, these are the unique variances as well. It tries to give you a proportion of variance accounted for. This is sort of meaningless. It does not follow the straight assumptions that we would end up having. It's sort of a holdover from the principal components regime. And our hypothesis test it gives us a chi-square of 161.14. That's our likelihood ratio test between this model and the saturated model. Has 35 degrees of freedom, but the p-value is very small, so we would reject the fit of the one-factor model. So I took the liberty to go and try this with two factors, and we reject. Try this with three factors. The p-value is getting a little bit bigger, but we still would reject with a type 1 error rate of 0.05. So with four factors, we see our p-value is 0.0512. So that tends to be where our solution would fit. So let's take a look at the four factor. And here, actually, this is not the four-factor solution. This is looking at the constraints themselves from each of these models, at least with the one factor, or just excuse me, the two factor, three factor, and four factor models. I formed the constraint matrix. So basically, I took the loading matrix, took the unique variance matrix, and made this matrix product. And I did this to show you that these diagonal matrices have very close to zero values, and they are off diagonal. This E negative 17 means you have to move that decimal place over 17 digits to the left. That thing's close to zero. So this is what's happening. This is how the model identifies the solution. So provides estimable parameter estimates. But again, you'll see the diagonal elements are allowed to have numbers that are bigger than zero, but all their off diagonals are constrained to zero. So looking at the four-factor solution, this is the pattern of loadings. And again, this is not rotated. And what R does is it eliminates the loadings that are statistically no different from zero. So basically, it forms a walled test. And if that walled test's p-value is large, it omits the loading, just showing you the pattern here. So what this shows us is factor one, all the item is measured by all the items. Factor two is measured by all but one. Factor three has several items that have positive loadings and several are negative. And then factor four only has three items measuring it, of which one is negative as well, too. Good luck describing that. So what ends up happening is this may be the initial solution of loadings, but it turns out we can rotate these loadings. We can do a mathematical transformation that should maintain the fit properties, but provide better interpretation. So the transformations to factor loadings are possible because the matrix of factor loadings is only unique up to this orthogonal rotation transformation. So if you don't like what you just saw, you can't explain it, rotate it. This is a problem with subjectivity in the analysis as well, too. Not a great sign. So historically, rotations use the properties of matrix algebra to adjust the factor loadings to more interpretable numbers. You would see this coming out from the principal component-based techniques. Now, I will note as we go later on, when we set our own constraints, setting things equal to zero, we lose the need to rotate our matrix. But that's not this analysis. Modern versions of rotations and transformations rely on something called target functions to specify what a good solution should look like, and they try to maximize the fit to the target itself. But again, the details of this modern approach are lacking in most textbooks, and what you end up seeing are rotation methods that are much from the 1960s or before. So there are two different types of classical rotation methods. And I say classical meaning the old methods. One is orthogonal. And again, orthogonal means perpendicular or correlations of zero. And these rotations that force the factor correlation to zero themselves. One of the most prevalent versions of this is something called Varimax. And then there is oblique rotations, rotations that allow for non-zero factor correlations. This most prevalent that we hear is the word Promax for this. And these also do estimate what we call an estimate of factor correlation itself. How this works mathematically is that if we have a rotation matrix here, I'm going to look at orthogonal rotation matrix to simplify this just a bit. If we have a rotation matrix T such that our new loadings are the product of our original loadings times this matrix, and again, orthogonal meaning that this thing is not just, when you multiply it by itself, either pre or post multiplying the transpose, you get the identity. Then you can easily show, well, I wouldn't say easily, but you can show in matrix algebra that if we replace, if we plug in the new loadings and we work the math through, we would end up seeing that the new loadings are really the old loadings times t. And then using a little matrix algebra, we could end up seeing that this t times t transpose by definition is identity, meaning that we have the same fit as the old loadings. This is my poor attempt to mathematically tell you that the rotations themselves, at least the classical ones, don't change the fit of the model. You still get the same model. You're just changing the interpretation of what the values happen to be. So modern versions of rotation are a little bit different. Again, they look for a target function. This is a target function looking for what we call simple structure, or where we have one loading that's positive per item, and they might use an optimization function to try to approximate this. So given the target function, rotations often seek to find this rotated solution that simultaneously minimizes the distance between your rotated solution and the original factor loadings, but fits best the target function. These rotation algorithms are often iterative, meaning they can fail to converge. And you often have to have multiple starts in mind to use the more modern methods as well, too. So this is a matrix of rotated factor loadings using a very old method, Varimax. Again, this is not saying that the factors are correlated again. Now, this solution provides numbers that are interesting, but again, hard to interpret. All of these are positive values. For the first dimension, you might see, item 9 and item 10 are very big in magnitude, but it's hard to interpret those. Plus, this assumes the factors are uncorrelated, which is also very difficult to assume in data like this. So what we can end up doing is looking at an oblique rotation. This is the one where we end up getting a factor correlation itself. Now, it provides a solution that also is somewhat hard to interpret. Again, the close to zero values of factor loadings have been omitted, and now you end up seeing that you have a chunk of 5 items loading onto factor 1, and one that positively, with items 9 and 10 again being high, whereas item 18 is negatively related to that. But factor 2 only has one item. That technically can't happen for this to be really identified. So again, this solution is a little bit weird and nonsense as well, and also very difficult to interpret. And then when you look at the factor correlation, you can see there's a very strong correlation between factor 1 and factor 2, but all the other correlations are negative, I guess, except for, of course, factor 3 and factor 4 are positively correlated. So this is a really weird solution as well. So exploratory factor analysis itself is very difficult to use and use well, and often it takes results that are confusing or hard to mint. And a lot of that is the problem with subjectivity. We subjectively apply a constraint we're not familiar with, and then we have to rotate results that we don't fully understand. I much prefer an approach where we take a confirmatory factor analysis method for it. We can conduct exploratory factor analysis using a CFA model. What we have to do, though, is to set the correct number of constraints needed for model identification. These constraints are typically imposed by taking the value of factor loadings for a few items on a few factors and setting them equal to 0. So basically, setting them to 0 allows you to say this item does not measure the factor. Now, other people will go and try to set them to other values. So for instance, we might make them like marker items. That's suggested in an old textbook by Brown. I prefer the 0 approach, meaning you're saying this item does not measure that factor itself. We can still keep the factor covariance matrix as an identity, although the more constraints we set, the more likely it is we can actually estimate a correlation or covariance as well. But these are how we set the model up. But there are some benefits to using confirmatory factor analysis for these models, exploratory analyses. CFA constraints remove rotational indeterminacy. You don't need to rotate afterwards, right? defines, so therefore it defines factors with potentially less ambiguity because the constraints are easy to see. This item does not measure this factor. You set that to begin with. And for some software, we get much better model fit information in SAS and SPSS, for instance. And also compared to the fact-anal function in R, we can do this in Lavaan, where we get all that model fit information and approximate fit information as well. So again, to do exploratory factor analysis with confirmatory factor analysis, you must either you must first fix a set of factor loadings to 0 or 1. I call this, or actually my mentor had called this row echelon form, where what we look at is what we do. If we have, let's imagine we have the 4-factor model that we saw previously in the EFA analysis. Dimension 1 would have all factor loadings estimated. In dimension 2, the first item would have a 0 for the factor loading on that factor, but the rest would be estimated. So basically, you're saying, oh, item 1 only measures factor 1, and then for dimension 3, the first and second items would have 0 loadings. The rest would be estimated, and then for dimension 4, the first, second, and third would have items with 0 factor loadings. The rest would be estimated. The term row echelon refers to sort of this triangle of zeros at the top right of your factor pattern matrix. We will also have to fix all the factor of covariances to 0, so the factors are uncorrelated, and fix all factor variances to 1. This is an identification method, the standardized factor approach. So then what we do is just run Lavaan. So for the 1-factor model, we can put this in syntax into Lavaan. The equal tilde defines the factor. You can look up the video on confirmatory factor analysis for more information on how to use Lavaan. We say all the items load onto that factor or are measured by that factor, and we use the CFA function to estimate this. We're using robust maximum likelihood for this as well, and we have to standardize our latent variable. That is, sets the factor mean and factor variance to 1. Now, you know, with 1 factor, we actually have no constraints in the loadings, so this is a standard 1-factor model we would run in the CFA anyway, and it will fit the same as we saw in the exploratory factor analysis with 1 factor as well. So here you have our information. If you remember the slide from the very first 1-factor model in EFA, the test statistic is the same here. The p-value is very close to 0, and there are 35 degrees of freedom. But added to this, we get better information about approximate fit. So now what we can see is the RMSEA for the 1-factor model is actually 0.048, which is actually quite good. Similarly, the comparative fit index and the Tucker-Lewis index are both above 0.95. So we would say this fits a 1-factor model quite well. And we would be able to stop here. We don't have to rotate things. And again, here's the value of all of this from the previous approach. Remember, 161.846 here is our test statistic, whereas this is slightly different, 161.14. But remember, in this original model, we had some missing data, whereas we don't have to remove the missing data in Lavaan. So those numbers aren't identical in this, but I would trust Lavaan more because we're using all the data that we have available to us. Now, because the 1-factor model fits so well, we could stop here. But CFA has more indices of model fit, which can make finding an appropriate solution easier. It also gives you standard errors for each factor loading, leading to a walled test to see if this is equal to 0, right? So here we can actually look at all of our factor loadings, see that those are non-zero, which is important. Now, even though we could stop here, we're going to continue on with the 2 and 3-factor versions to see what this looks like. So to look at 2 factors, we can add factor 2 here. Now, item 1 will have a 0 loading, so we don't include it on the line for factor 2. So item 1's factor 2 loading is set to 0, and we have all the other variables on there estimating loadings. And we also have to set the covariance between the factors to 0. This should be a double tilde there. My apologies. That should be double tilde for covariance right there. When we estimate it, here is what we end up getting. Double tilde for the regression implies the covariance should be 0 as well, too. So this should fit the same. What we end up seeing here is our model fit gets even better. Our RMSEA is 0.023. We want this, again, to be less than 0.05. It certainly is. Our CFI and TLI are very close to 1. So we still improve our model fit. But now if we look at our estimates, this is where we can really try to make sense. Again, all of our estimates are about the same range and positive on factor 1, and they're all significant. But when we get to factor 2, take a look at the significance of it. we can have a bunch of estimates that are non-significant now, leaving us only with item 13, 18, 21, and 23. So if we really wanted to define what factor 2 meant, we can go back to those items and try to figure out if there's something common to them for factor 2. I won't do that for right now, because that is very subjective. And here are the 3-factor results. Again, the RMSEA gets better. CFI and TLI are still a little bit better. And now when we see this is where things go a little off the rails. Factor 1 has all the loadings significant, but factor 2's loadings, none of them are significant. And factor 3's loadings, none of those are significant. So what's this telling us? This is telling us that, yeah, we could estimate 3 factors, but the factor loadings are so weak and probably not very different from 0 that factors 2 and factor 3 aren't going to mean a whole lot. Yet again, reinforcing our 1-factor solution. So, to wrap up, this lecture was a discussion about the world of exploratory factor analysis and principal components analysis. And what we showed was the following: that principal components analysis, the very beginning, is great for data reduction, right? Reducing the number of variables in a data set. However, that's also what gets used when people use exploratory factor analysis, and it shouldn't be. Maximum likelihood methods for exploratory factor analysis are better picks. They're likelihood based, but they employ hidden constraints and often are implemented in ways that are difficult to use, don't have all the model fit statistics, or have some curious choices for their design. Maximum likelihood EFA can also be shown to be equal to CFA for certain models, which is great. And overall, to me, confirmatory factor analysis is still your best bet for how to do this. And finally, one last note. A lot of times you will see papers where people are describing the estimation of a model. Let's say they have a brand new scale and they're describing its properties in a research study, a journal article. And a lot of times you'll see someone do a confirmatory factor analysis and then an exploratory factor analysis. I don't like that. Now, sometimes those converge to the same result. That's fine when it does, but when it doesn't, you can't conclude that one is better than the other. In fact, if you were to conclude that, you would just pick CFA in the first place, because the PCA version of EFA, those aren't EFA models, those are approximations. And ML EFA we saw has a lot of drawbacks as well. So that's the lecture. Thank you for listening. Onward.